You may have heard about polarized light in chemistry. As we've said before, light has oscillating B and E fields. Now most of the light we see doesn't line up neatly, so we can have B and E in all sorts of directions, as long as they're perpendicular to each other. So let's just represent light by looking just at E. Well, if we use just E, we can describe the electric field in unpolarized light as being in every direction. We can break this into just X and Y components and represent it like this. Now, how we can take this unpolarized light to make it polarized light is the question. So if we add a filter in front of some kind of polarized or unpolarized light, we can actually screen out certain electric fields that can come through. So here, if we have some diagonal electrical field and we go through this filter with some angle between the filter lines and the field itself, we'll only get out the component that's in the same direction as this filter. So we end up with a slightly smaller amount of light coming through in the same direction as the previous filter. Now let's say we have a perpendicular filter that's directly next to this light. Now the angle between these two is 90 degrees. There's no component of light that's in the same direction as this filter. So it turns out on the other side we would just get no light. Mathematically, we can represent polarization using Malus's law. The intensity of the light coming out of the filter depends on the intensity of the light going into the filter and cosine of the angle between those two. For example, if I had some polarized light with an angle of 60 degrees relative to the filter, I end up with half of the intensity because I plug in 60 here and see that that comes out to making a half. Now notice if you have unpolarized light go through one filter, we knock out the amount that's not in the same direction. In this case, unpolarized light going through a filter will always knock out exactly half so that we get just one component.